Imagine a creature so small that it could walk on the tip of your finger but strong enough to carry objects up to 50 times its own weight. If humans had the same strength-to-size ratio, we would be able to lift cars as if they were toys. But how do ants achieve this impressive feat? Is it just muscle strength, or is there a hidden science behind this incredible power? In this video, we'll dive into the world of ants and uncover the secrets of their immense strength. We'll explore the biomechanics of their bodies, their incredible cooperation strategies, and the evolutionary adaptations that have turned them into the ultimate weightlifters of the insect world. From physical mechanisms to collective intelligence, every aspect of an ant's life holds fascinating mysteries. And what if I told you that this strength is not just a random quirk of nature, but the result of millions of years of refined evolution? Science is beginning to unravel the details behind what makes ants so powerful, and some of these discoveries could even influence human technologies in the future. Get ready, because by the end of this video, you'll never look at ants the same way again. If you've ever been amazed by the sight of an ant carrying something much larger than itself, what comes next will leave you completely speechless. Let's begin this journey into the world of superpowered ants. At first glance, it seems impossible for such a tiny creature to carry such heavy loads. However, the answer to this mystery lies in the physics of scale. As a living being gets smaller, the relationship between its mass and its muscle strength changes dramatically. This means that, proportionally, smaller creatures have much greater relative strength than larger ones. To understand this better, think of an elephant and an ant. The elephant is strong, but it cannot lift 50 times its own weight. This happens because muscle strength is directly related to the cross-sectional area of the muscles, while weight is related to the total volume of the body. Since the ant has a small body, its musculature has a huge advantage relative to its total weight. Another crucial factor is the ant's exoskeleton, made of chitin. This material is lightweight yet extremely strong, functioning as a natural armor that protects the body without compromising mobility. Thanks to this structure, ants can withstand extreme loads without collapsing under their own weight, something vertebrates like us could never achieve. Additionally, an ant's mandibles play an essential role. They don't just grip objects. They function as biomechanical levers, allowing ants to lift heavy loads with less effort. This same principle is used by engineers to create more efficient mechanical systems, proving that nature has mastered the art of engineering for millions of years. To top it off, ants use a trick that few people know about. They distribute weight throughout their entire body, adjusting their posture and using all 6 legs to balance the load. This precise postural control ensures that the weight is evenly distributed, preventing falls or loss of balance while transporting massive objects. Many people might think that ants are just tiny natural bodybuilders, but their strength doesn't come from muscles alone. One of the biggest secrets to their power lies in the energy efficiency of their metabolism, which allows them to sustain this effort for long periods without exhausting themselves. Unlike mammals, ants don't have lungs. Instead, they breathe through a network of small tubes called tracheae, which deliver oxygen directly to their muscles. This eliminates the need for a highly developed circulatory system, reducing energy expenditure and allowing energy to be used more efficiently. Additionally, ants have an incredibly optimized metabolism for endurance. While a human quickly tires when carrying heavy weights, ants can sustain the effort for hours without signs of exhaustion. This is one of the factors that make them so efficient in foraging and nest building. Another fascinating point is that ants adjust the force applied according to the terrain. If they are carrying a leaf over rough ground, they alter their leg positions to ensure greater stability. This fine adjustment, made almost automatically, ensures that they don't lose control of the load, even on inclined surfaces or over obstacles. And here's a surprising detail. When an ant realizes the load is too heavy, it releases chemical signals to call for reinforcements. This means that, in addition to physical strength, ants use collective intelligence to overcome challenges, making them even more efficient. If a single ant is already incredibly strong, imagine hundreds or thousands of them working together. The real secret to ant success lies in their ability to cooperate. Different species have developed unique strategies for transporting massive objects in a coordinated manner. One of the most impressive examples is army ants, which create living bridges with their own bodies to cross obstacles. These temporary structures allow the rest of the colony to pass over with ease, ensuring that food collection is never interrupted. Leafcutter ants, on the other hand, have developed an assembly line system where each individual plays a specific role. Some cut leaves, others carry them, while a third group protects the workers from potential predators. This efficient organization makes the colony incredibly productive. Another fascinating behavior is how some ants work together to drag enormous objects. They constantly adjust their positions to ensure the weight is evenly distributed. This micro-adjustment system allows the load to be moved with minimal effort. And the most impressive part? All of this happens without a central leader directing the operation. The coordinated behavior of ants is governed by chemical signals called pheromones, which guide their actions and ensure that each one knows exactly what to do at the right moment. Ants don't just carry massive loads. They also design highly efficient transport strategies. Different species have developed specialized methods to optimize the movement of heavy loads, whether on steep terrain, underground tunnels, or even in water. Their complex organization resembles human logistics systems, except without the need for supervision or advanced technology. One of the most remarkable examples is leafcutter ants, which transport leaf fragments methodically. They follow specific chemical trails and create true highways through vegetation, minimizing unnecessary effort. If an ant detects congestion on a path, it simply changes direction to avoid excessive traffic. This behavior is so effective that it has inspired research to improve urban transportation systems and distribution networks. Another fascinating case occurs inside underground ant nests. Some species construct strategically sloped tunnels to reduce resistance when moving heavy loads. These structures follow patterns that maximize ventilation and ensure safe routes for food transport. And if you think ants only carry objects on solid ground, think again. Some species, like fire ants, can form living rafts using their own bodies. During floods, they link together to create floating platforms, protecting the queen and eggs while navigating the waters in search of a new safe location. Ants' ability to carry enormous weights didn't just appear out of nowhere. This superpower is the result of millions of years of evolution, refining their body structures, muscles, and social behavior. Natural selection favored those that could move food more efficiently, ensuring their colony had a greater chance of survival. The ancestors of ants emerged over 140 million years ago, during the age of the dinosaurs. In the beginning, they weren't as organized or as strong as they are today, but over time, the individuals that were more efficient at gathering and transporting food began to stand out. These advantageous traits were passed down through generations, shaping the modern ants we know today. Another crucial factor in this evolution was environmental pressure. Species living in tropical forests had to develop strategies to transport loads through difficult terrain, while those in deserts had to find ways to carry heavy objects without wasting energy under extreme heat. Each adaptation resulted in an even more efficient way to handle environmental challenges. Additionally, cooperation became a major evolutionary advantage. The first ants that started working together had a higher chance of success in foraging and defending against predators. This led to the development of highly organized societies where each individual contributes to the colony's well-being. Over time, the ants that communicated and worked together the best became the dominant species. And it's not just strength that has evolved. Ants' bodies have undergone structural changes too. Their muscles have become more compact and efficient, their mandibles have developed stronger mechanisms, and their legs have been adjusted to ensure maximum traction. Today, ants are a perfect example of how evolution can transform small insects into true powerhouses of strength and efficiency. Ants intrigue scientists not only because of their strength but also for their intelligence and organization. Studies on these insects have been helping humanity develop new technologies, from robots inspired by their behavior to algorithms based on their food-searching strategies. One of the fields most impacted by these studies is robotics. Researchers have developed small robots that mimic how ants coordinate their movements when carrying heavy loads. These autonomous robots can be used in rescue missions, space exploration, and even in the construction of structures in hard-to-reach locations. Another area that has benefited is logistics. Companies study ant behavior to create more efficient distribution networks. The method ants use to find the shortest path between food and their nest, for example, has inspired improvements in GPS navigation algorithms and large-scale delivery systems. Medicine has also gained insights from ants. Scientists are investigating how fire ants resist infections despite living in bacteria-filled environments. The answer could lead to the development of new antibiotics or treatments for drug-resistant infections. And here's a surprising detail. Scientists have already managed to create artificial ant colonies in laboratories to study their biomechanics in detail. These experiments reveal crucial information about how their legs, mandibles, and muscles function, opening doors to new discoveries in biotechnology. Ants are true titans of nature. Their small size might be deceiving, but their strength results from an incredibly efficient biomechanical design and millions of years of evolution. From their powerful mandibles to their logistical strategies, every detail of their behavior showcases how astonishing nature can be. What's even more impressive is that their strength isn't just physical. Ants also use collective intelligence to coordinate tasks, creating systems that rival the most advanced human technologies. Their teamwork, adaptability, and complex organization prove that it's not just about muscles, it's about strategy. Now we want to hear from you. What was the most surprising thing you learned about ants today? Leave your comment below. And if you enjoyed this deep dive into the world of these tiny giants, don't forget to like, subscribe, and turn on notifications for more incredible content about the natural world. Thanks for watching, and see you in the next video.